I agree that the importance of having low impedance to earth is often overstated, especially when it comes to grounding systems for buildings. A well-designed and installed grounding system is much more important than low impedance to earth. NFPA 70E, Standard for Electrical Safety in the Workplace, does not specify a minimum resistance or impedance for grounding electrodes. It simply states that the grounding electrode system shall be installed in accordance with the requirements of the National Electrical Code, or NEC. The NEC requires that grounding electrodes be installed in a manner that will ensure a permanent and effective ground. It does not specify a minimum resistance or impedance for grounding electrodes. IEEE Standard 81.2012 Guide for Measuring Earth Resistivity, Ground Impedance, and Soil Resistivity states that the resistance of a grounding electrode is not a reliable indicator of its ability to dissipate ground fault current. It recommends that grounding electrode systems be designed and installed based on the requirements of the NEC. The most important factor when it comes to grounding systems is to ensure that the system is properly designed and installed. This includes using the correct materials, sizing the grounding conductors correctly, and ensuring that the grounding electrodes are properly bonded together. Once the grounding system is properly installed, the resistance or impedance to earth is not as important as many people believe. The subject of grounding is complex and can be difficult to understand. It is important for electrical engineers to have a good understanding of grounding principles in order to design and install safe and effective grounding systems. Now, let's delve into the intricacies of grounding systems and the often misunderstood concept of low impedance to earth. Grounding, in essence, is the intentional connection of electrical systems and equipment to the earth. Its primary purpose is to provide a safe path for fault currents to return to the source, thereby minimizing the risk of electric shock and fire. There are several key aspects to consider when evaluating the importance of low impedance to earth. Firstly, let's clarify the difference between resistance and impedance. Resistance is the opposition to the flow of direct current, while impedance is the opposition to the flow of alternating current. Impedance takes into account both resistance and reactance, which is the opposition to current flow due to capacitance and inductance. In grounding systems, we are typically dealing with alternating current, so impedance is the more relevant parameter. Secondly, the NEC, which is the primary standard for electrical installations in the United States, does not mandate a specific minimum resistance or impedance value for grounding electrodes. Instead, the NEC focuses on ensuring a permanent and effective ground. This means that the grounding system must be designed and installed in a way that provides a reliable low impedance path for fault currents. The NEC outlines various requirements for grounding electrodes, including their type, size, and installation depth. Common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes, also known as UFA grounds. The NEC also specifies requirements for the grounding electrode conductor, which connects the grounding electrode to the electrical system. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Thirdly, IEEE Standard 81.2012 provides guidance on measuring earth resistivity, ground impedance, and soil resistivity. This standard emphasizes that the resistance of a grounding electrode is not a reliable indicator of its ability to dissipate ground fault current. The reason for this is that the resistance of the grounding electrode is only one component of the overall impedance of the grounding system. The impedance of the grounding system also includes the impedance of the soil surrounding the grounding electrode, as well as the impedance of the grounding conductors and connections. Therefore, a low resistance grounding electrode does not necessarily guarantee a low impedance grounding system. Fourthly, the effectiveness of a grounding system depends on several factors, including the soil resistivity, the type and size of grounding electrodes, the depth of installation, and the quality of connections. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable because it allows fault currents to dissipate more easily into the earth. Soil resistivity varies depending on the type of soil, its moisture content, and its temperature. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to install chemical ground rods to improve the effectiveness of the grounding system. Fifthly, the primary goal of a grounding system is to provide a low impedance path for fault currents to return to the source. This allows the overcurrent protective devices, such as circuit breakers and fuses, to quickly detect and interrupt the fault, thereby minimizing the risk of electric shock and fire. The lower the impedance of the grounding system, the faster the overcurrent protective devices will operate. However, there is a point of diminishing returns. Reducing the impedance of the grounding system below a certain level will not significantly improve the performance of the overcurrent protective devices. Sixthly, in some cases, low impedance to earth can actually be detrimental. For example, in sensitive electronic equipment, a low impedance ground can create ground loops, which can cause noise and interference. Ground loops occur when there are multiple ground paths between two pieces of equipment. These multiple ground paths can create a circulating current, which can induce noise into the signal circuits. To avoid ground loops, it is important to use a single-point grounding system where all equipment is grounded to a common point. Seventhly, lightning protection systems are designed to protect buildings and equipment from lightning strikes. Lightning strikes can generate extremely high currents, which can cause significant damage to electrical systems and equipment. Lightning protection systems typically include air terminals, which are installed on the roof of the building to intercept lightning strikes, down conductors, which carry the lightning current to ground, and grounding electrodes, which dissipate the lightning current into the earth. In lightning protection systems, low impedance to earth is more important than in ordinary grounding systems. This is because lightning currents are very high frequency, and high-frequency currents tend to follow the path of least impedance. However, even in lightning protection systems, it is more important to have a well-designed and installed system than to simply focus on achieving a low impedance to earth. NFPA 780, standard for the installation of lightning protection systems, emphasizes the importance of bonding all grounded metal objects together to minimize the risk of side flashes. Side flashes occur when lightning current jumps from one grounded object to another. Eighthly, the design and installation of grounding systems should be performed by qualified electrical engineers or electricians who have a thorough understanding of grounding principles and the requirements of the NEC and other applicable standards. It is important to use the correct materials and methods to ensure that the grounding system is safe and effective. Regular inspection and testing of grounding systems is also essential to ensure that they are functioning properly. Ninthly, the concept of a magical 1 ohm resistance to earth is a misconception. There is no scientific basis for this requirement. The NEC does not specify a minimum resistance or impedance value for grounding electrodes, and IEEE Standard 81.2012 states that the resistance of a grounding electrode is not a reliable indicator of its ability to dissipate ground fault current. The focus should be on designing and installing a grounding system that meets the requirements of the NEC and other applicable standards, and that provides a reliable low impedance path for fault currents. Tenthly, when designing a grounding system, it is important to consider the specific application and the type of equipment being grounded. For example, sensitive electronic equipment may require a different grounding approach than industrial equipment. It is also important to consider the environmental conditions, such as soil resistivity and the presence of corrosive materials. In summary, the importance of having low impedance to earth in grounding systems is often overstated. A well-designed and installed grounding system that meets the requirements of the NEC and other applicable standards is much more important than simply achieving a low impedance to earth. The focus should be on ensuring that the grounding system provides a reliable low impedance path for fault currents, and that it is properly maintained and tested. The NEC is the National Electrical Code. IEEE is the Institute of Electrical and Electronics Engineers. NFPA is the National Fire Protection Association. Grounding is the connection of electrical equipment to the earth. Impedance is the opposition to the flow of alternating current. Resistance is the opposition to the flow of direct current. Soil resistivity is a measure of how well the soil conducts electricity. Ground loops are unwanted current paths that can cause noise and interference. Side flashes are sparks that can occur when lightning current jumps from one grounded object to another. Overcurrent protective devices are devices that protect electrical circuits from overcurrents. The NEC provides specific requirements for grounding electrode systems, including the types of electrodes that are permitted, their size, and their installation depth. Common grounding electrodes include ground rods, ground plates, and concrete encased electrodes. Ground rods are typically driven into the earth vertically, while ground plates are buried horizontally. Concrete encased electrodes are typically installed in the footing of a building. The NEC also specifies requirements for the grounding electrode conductor, which connects the grounding electrode to the electrical system. The size of the grounding electrode conductor is based on the size of the service entrance conductors. The NEC also requires that all metal objects that are likely to become energized be bonded together and connected to the grounding system. This includes metal conduits, metal enclosures, and metal equipment frames. Bonding helps to ensure that all metal objects are at the same potential, which reduces the risk of electric shock. IEEE Standard 81.2012 provides guidance on measuring earth resistivity, ground impedance, and soil resistivity. This standard recommends the grounding electrode systems be designed and installed based on the requirements of the NEC. This standard also provides guidance on how to measure the resistance and impedance of grounding electrodes. The resistance of a grounding electrode can be measured using a ground resistance meter. The impedance of a grounding electrode can be measured using an impedance meter. When designing a grounding system, it is important to consider the soil resistivity at the site. Soil resistivity varies depending on the type of soil, its moisture content, and its temperature. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to install chemical ground rods to improve the effectiveness of the grounding system. Chemical ground rods are ground rods that are filled with chemicals that help to reduce the soil resistivity around the rod. Regular inspection and testing of grounding systems is essential to ensure that they are functioning properly. Grounding systems should be inspected visually for any signs of damage or corrosion. The resistance and impedance of grounding electrodes should be measured periodically to ensure that they are within acceptable limits. If the resistance or impedance of a grounding electrode is too high, it may be necessary to replace the electrode or to improve the grounding system. Grounding systems are an essential part of electrical safety. A well-designed and installed grounding system can help to protect people from electric shock and prevent fires. Low impedance to earth facilitates effective fault current return. Proper bonding minimizes potential differences. Regular inspections ensure system integrity. Compliance with NEC and IEEE standards is crucial. Grounding is a multifaceted topic with a deep reliance on following and implementing NEC standards and a general understanding of IEEE Standard 81.2012, which will better equip one in providing optimal safety to people and equipment. In the realm of electrical engineering, grounding systems serve as the unsung heroes, diligently working to safeguard lives and property from the hazards of electrical faults. While the concept of low impedance to earth often takes center stage in discussions about grounding, it's crucial to recognize that a holistic approach, encompassing meticulous design, proper installation, and adherence to industry standards ultimately determines the effectiveness of a grounding system. Now let's explore some other critical elements to consider when evaluating grounding systems. Firstly, surge protection devices, or SPTs, play a vital role in mitigating transient overvoltages caused by lightning strikes, utility switching, and other electrical disturbances. SPT are designed to divert these surges to ground, preventing them from damaging sensitive electronic equipment. The effectiveness of SPD depends on a low impedance grounding path to facilitate the rapid dissipation of surge currents. Secondly, the location of grounding electrodes significantly impacts their performance. Electrodes placed in areas with consistently moist soil tend to exhibit lower resistance compared to those in dry or rocky terrain. Furthermore, proximity to underground metallic structures such as water pipes can influence the effectiveness of grounding electrodes. Thirdly, Exothermic welding, also known as CAD welding, provides a superior method for creating permanent, low-resistance connections between grounding conductors. Unlike mechanical connections that can loosen or corrode over time, exothermic welds create a molecular bond, ensuring long-term reliability. Fourthly, the use of ground-enhancing materials, or GEM, can improve the conductivity of soil surrounding grounding electrodes, particularly in areas with poor soil conditions. GEN typically consists of a mixture of conductive minerals and aggregates that increase the contact area between the electrode and the earth. Fifthly, equipotential bonding creates a network of interconnected grounding conductors that equalize potential differences between various metallic objects within a structure. This reduces the risk of electric shock by minimizing the voltage gradient between accessible surfaces. Sixthly, grounding systems should be periodically inspected and tested to verify their integrity and effectiveness. Visual inspections can identify signs of corrosion, damage, or loose connections, while earth resistance testing can assess the overall performance of the grounding system. Seventhly, the selection of appropriate grounding conductors is critical for ensuring adequate fault current carrying capacity. Grounding conductors should be sized based on the available fault current and the clearing time of overcurrent protective devices. Eighthly, isolated ground systems are sometimes used in sensitive electronic environments to minimize noise and interference. In an isolated ground system, a separate grounding conductor is run directly from the equipment to the main grounding electrode, avoiding common ground paths with other equipment. Ninthly, understanding the difference between system grounding and equipment grounding is essential for designing effective grounding systems. System grounding refers to the grounding of the electrical system's neutral point, while equipment grounding refers to the grounding of non-current carrying metal parts of equipment. Tenthly, grounding systems should be designed to accommodate future expansion or modifications. Adequate space should be provided for adding additional grounding electrodes or conductors as needed. In conclusion, the design and implementation of effective grounding systems require a comprehensive understanding of electrical principles, industry standards, and best practices. While low impedance to earth is an important consideration, it should not be the sole focus. A holistic approach that encompasses proper design, installation, maintenance, and testing will ensure the safety and reliability of electrical systems.